I'm going to build the ugliest distribution I can. 2 separate humps, nothing in the middle, completely asymmetric. Nothing about it is normal. Now, I take 30 values from it at random and write down their average. Then I do that again, and again 10,000 times. And when I plot those 10,000 averages, I get a perfect bell curve from data that looks like this. That result is called the central limit theorem, and it is, I think, the strangest true thing in statistics. This is the episode that explains why the previous one mattered. Today, why averages behave so differently from the things being averaged, how to see it happen on 3 completely different starting distributions, the formula for how much the spread shrinks, and, importantly, the conditions under which the whole thing quietly stops working. Here's the thing to hold on to first. A sample mean is itself a random variable. That sounds like a technicality, but it's the entire idea. If I sample 30 people and average their heights, I get a number. If you do it, you get a different number. That average has its own distribution, its own spread, its own shape, and that shape is not the same as the shape of the thing you sampled. And this is exactly where intuition goes wrong. People assume that if the underlying data is skewed, the averages will be skewed too, that the shape somehow gets inherited. It doesn't. The averaging process actively destroys the original shape, because for an average to land far from center, many independent values all have to be extreme in the same direction at once. And that's overwhelmingly unlikely no matter what shape they came from. Let's set it up so we can watch. We generate a big pile of samples arranged as a grid, 10,000 rows, each row holding 30 draws. Then we take the mean along each row. That gives us 10,000 sample means. One number py call for the data, 1 for the averaging, and the axis equals 1 argument is what says average across each row rather than down each column. Here's the whole experiment in 2 lines. Generate, then average along axis 1. The important part is that we can swap the first line for any distribution we like, uniform, exponential, our 2-humped monster, and leave the second line completely untouched. That's the claim we're testing. The output shape shouldn't care about the input shape. So let's start with uniform. Flat, no peak, every value between 0 and 1 equally likely. It looks nothing like a bell. We average 30 at a time, and there it is. Symmetric, peaked in the middle, tails falling away. Uniform in, bell curve out. Now the exponential distribution, which is aggressively lopsided, piled up at 0 with a long tail to the right. Average 30 of those, and again a bell. And finally the bimodal monster from the cold open, 2 humps, a hole in the middle. Average 30, a bell. 3 completely unrelated starting shapes, 1 destination. There's also a precise statement about how tight that bell is. The standard deviation of a sample means equals the original standard deviation divided by the square root of the sample size. Sample 4 at a time, and the spread halves. Sample 100, it's 10 times tighter. That's the same square root law from episode 1. And it's the reason a poll of 1,000 people can describe a country of 60 million. This is what licenses most of statistics. It's why you can build a confidence interval around a mean without knowing what distribution your data came from. It's why hypothesis tests on averages work on messy real-world data. And practically, if you're averaging roughly 30 samples is the usual rule of thumb for the bell to be a good approximation, though mildly skewed data often gets there by 10. Now the honest part, because the CLT is routinely overclaimed, it needs the samples to be independent. So, time series with autocorrelation break it. It needs finite variance, and some real distributions like the Cauchy don't have one, so averaging them achieves literally nothing. The average of 1,000 is as noisy as a single value. And with severe skew, 30 is nowhere near enough. You may need thousands. The theorem is about the limit. It says nothing about how fast you get there. One sentence. Averages converge to a bell curve almost regardless of what you averaged, which is why we could do statistics on data whose distribution we never identified. Now we have the machinery to ask a real question. If I run an experiment and see a difference, how do I know whether that difference is real or just the kind of thing randomness produces on its own? Next episode.